Welcome, class 10. Today's topic is principle of a machine. So let's say that there is a simple machine where at one end we apply the effort, then in the other end we get the load. So the point where the effort is applied is called the effort point, and the point where the load is applied is called the load point. So here this is the effort point and this tip is called the load point. So at the effort point, we apply the input energy. Now the input energy must be equal to the work done on the effort point. So at this point, if any work is done, then that will be equal to the input energy. Now since we are talking about work done, then it has to be force into displacement. So work done in this case will be effort, that is the force, okay, into displacement of the effort point. So how much this effort point will be displaced, that multiplied with the effort, that is the amount of force applied, will be the work done. So this can be represented as E for effort and multiplied with DE. DE represents displacement of the effort point. Similarly, at the load point, we will get the output energy. Now, this output energy must be equal to the work obtained at the load point. So, at this point, the work obtained must be equal to the output energy. And again, here also, we are talking about work done or work obtained, that must be equal to the force into displacement. Here, the force will be called as load and it is getting multiplied with the displacement of the load point. So, how much the load point will move, that displacement multiplied with the force named load will be uh, uh, will give us the work obtained at the load point. So this is represented as L for the load multiplied by DL, that is the displacement of load point. Now in any case, if we apply a certain amount of input energy and that becomes equal to the output energy, so the input energy and output energy must be equal. In no case output energy becomes greater than the input energy, because if you are applying input energy and if you are getting more than that the output energy, then here the law of conservation of energy will be violated. So here the input energy and output energy must be equal, and this equal, this case of having the input energy being equal to output energy is always in the case of ideal machine. Ideal machine means it is only in the case of a machine which is theoretically possible. Okay, so input energy becomes equal to output energy in the case of ideal machine, where the efficiency of this machine will be equal to 100%. But in actual machine, practically when we talk about the actual machine, the efficiency is not always equal to 100%. So that means the input energy in actual machine, whatever input energy is given is provided to the machine, the same amount of output energy is not obtained. So in that case the efficiency becomes less than 100%. Over here in actual machine, some amount of energy is always lost in order to overcome friction or gets converted into heat, light, and sound energy. So, this lost energy, because it's lost in order to overcome friction, and some energy gets converted into heat or light or sound energy. Therefore, the input energy, if you provide in a machine, the same amount of output energy won't be at the output end or at the load point. Suppose if we say if a machine is said to be 70% efficient, then this means that only 70% of total energy supplied to the machine is effectively used and is obtained as useful output energy. So the remaining 30% of the energy is lost in the form of heat, light, or sound energy. Okay, heat energy for example, if we use any machine and over the period when the work is done, the machine gets heated up, and we all know that it may produce sound energy as well, and in some cases you may even see the sparks of light. So this means that some amount of energy provided to the machine is lost in the form of heat, light, or sound energy, or maybe some other forms of energy as well. Next is relationship between efficiency, mechanical advantage, and velocity ratio. We have all learned earlier that efficiency, in this case it's the Greek letter which represents efficiency, it's called eta. So efficiency, or eta, is equal to work output by work input. This is what we have learned in the previous video. So now earlier we have learned that work output, that is equal to the load into the displacement of the load point, and the work output is equal to the effort into the displacement of the effort point. So here we can split this L and E, and we can write separately L by E into dl by dE this way. And since L by E is represented by mechanical advantage and dl by dE, the reciprocal of dl by dE, that is dE by dl, is equal to the velocity ratio. That means displacement of effort arm by displacement of load arm will be equal to the velocity ratio. So here LE can be replaced by MA, the mechanical advantage, and dl by dE can be replaced by VR, that is inverse of VR, 1 by VR. So here if we cross multiply VR with efficiency and MA is left out in the right hand side, then we'll get the mechanical advantage becomes equal to the velocity ratio into efficiency eta. So we can say from this that mechanical advantage is the product of its efficiency and velocity ratio. So this is the required relationship between mechanical advantage, velocity ratio, and efficiency.